Hello everyone, welcome to our operating system lecture. In this video, we are going to learn one of the most important concepts in process synchronization, semaphores. When multiple processes execute simultaneously and access the same resource, we need a mechanism to control that access. Otherwise, we may get incorrect or unpredictable results. In this lecture, we will understand critical sections, race conditions, semaphore operations such as wait and signal, binary and counting semaphores, and system V semaphore functions in C. We will look at the real life example and some Viva questions. Let us begin. Before we start, let us see what we are going to learn. At the end of the session, you should be able to explain what a race condition is and identify critical section. We will be able to define a semaphore and explain the wait and signal operations. We will differentiate between binary semaphore and counting semaphore. We will also compare semaphore with a mutex. Then we will trace a simple synchronization example step by step. Finally, we will understand important system V semaphore functions used in C program. Before defining a semaphore, let us understand why actual need one. Consider two processes P1 and P2. Before both the processes are accessing the same bank account, consider two processes P1 and P2. Both processes are accessing the same bank account. Suppose the current balance is 1000 rupees. Process P1 wants to deposit some money while process P2 wants to withdraw some money. Now think about this question. What will happen if both processes read and modify the balance at exactly the same time? This situation can produce an incorrect result balance because both processes are accessing shared data concurrently. This problem leads us to something called a race condition. A race condition occurs when two or more processes access shared data concurrently, and the final result depends on the order in which those processes execute. Let us see an example. Initially, the balance is 1000 rupees. P1 reads the balance as 1000. Before P1 finishes its operation, P2 also reads the balance as 1000. Suppose P1 adds 100 and writes 1100. But P2 uses the old value of 1000, subtracts 100 and writes 900. Now the final balance becomes 900. P1 update has effectively been lost. This is called a lost update, and it is one of the example of race condition. Therefore, we need to make sure that only one process modifies the shared data at a time. The portion of a program where a process accesses shared data or a shared resource is called the critical section. A typical process can be divided into four sections. First, the entry section. Here the process requests permission to enter the critical section. Next is the critical section, where the shared resource is accessed. After completing the operation, the process enters the exit section, where it releases the resources. Finally, the process continues with its remainder section. A good critical section solution should satisfy important properties such as mutual exclusion, progress, and bounded waiting. For our current discussion, remember one important point. Only one process should be allowed inside a protected critical section at a time. One mechanism that helps us achieve this is a semaphore. Now let us define a semaphore. A semaphore is a synchronization mechanism used to control access to shared resources by multiple processes or threads. You can think of a semaphore as maintaining a number of permits. A process must obtain a permit before accessing a protected resource. After completing its work, it returns a permit. A semaphore primarily provides two atomic operations. They are wait and signal. The wait operation attempts to acquire the resource. The signal operation releases the resource or indicates that the resource is available again. An important word here is atomic. An atomic operation is completed as one of individual operation. Another process cannot interfere halfway through a semaphore operation. Let us understand wait and signal with a simple example. Suppose semaphore S is initialized to 1. Process P1 executes wait of S. Because the semaphore is available, P1 obtains the permit and the semaphore value effectively becomes 0. P1 now can enter the protected section. While P1 is working, suppose P2 executes wait of S, the resource is not available, therefore P2 has to wait. After completing this work, P1 executes signal of S. The permit becomes available again, allowing a waiting process such as P2 to continue. So remember this simple idea. Wait means request or acquire. Signal means release or notify. There are two major types of semaphores. The first is a binary semaphore. A binary semaphore typically operates with two states, commonly represented using 0 and 1. It is useful when only one process should access a protected resource at a time. For example, consider a single printer shared by multiple processes. Second type is a counting semaphore. A counting semaphore is useful when multiple instances of the same resource are available. For example, suppose a computer lab has 5 identical printers. The semaphore can be initialized to 5. Each process that obtains a printer reduces the number of available permits. When a printer is released, the permit is returned. Here is a quick question. A parking lot has 10 spaces. What should be the initial semaphore value? The answer is 10. Let us understand counting semaphore using parking lot example. Imagine a parking area with 5 parking spaces. Initially, all 5 spaces are available. So we initialize the semaphore value to 5. When one car enters, it occupies one parking space. Conceptually, it performs a wait operation. The number of available permits decreases from 5 to 4. When another car enters, it decreases again. Eventually, if all parking spaces are occupied, the semaphore reaches 0. Now, another arriving car cannot obtain a parking space and must wait. When a car leaves the parking area, it performs the equivalent of a signal operation. One permit becomes available, a waiting car can then enter. This is a basic idea behind a computing counting semaphore. What is the difference between semaphore and a mutex? A mutex is primarily a ownership-based locking mechanism. A thread or process locks the mutex before entering the protected section and should unlock the mutex after completing its operation. A semaphore, on the other hand, is based on permits or signaling. A semaphore can also represent multiple resources using a count. Another important difference is ownership. With a mutex, a task that acquires the mutex is normally expected to release it. A semaphore does not have the same ownership semantics. One task can wait and another task can signal, which makes semaphores useful for event ordering and synchronization. So remember, mutex think ownership and locking, semaphore think signaling and permit. Now let us see how a semaphore can protect a critical section. We initialize a binary semaphore called a mutex with a value 1. Before entering the critical section, the process performs wait of mutex. If the permit is available, the process enters. Suppose it modifies some shared data while this process is inside the protected region. Another process attempting to acquire the semaphore will have to wait. After completing the operation, the first process performs signal of mutex. Now the another waiting process can proceed. In this way, a semaphore can provide mutual exclusion. One of the classical synchronization problem in operating system is the producer-consumer problem. Here we have a producer, a consumer, and a shared buffer. The producer creates the data and places it into the buffer. The consumer removes the data from the buffer. Suppose the buffer has n positions. We can use three synchronization variables. Empty represents the number of empty buffer position and is initially n. Full represents the number of occupied positions and it is initially 0. Mutex initialized to 1. Protect access to the shared buffer. The producer must make sure that an empty position exits before inserting an item. The consumer must make sure that an item exists before removing one. This is an important practical application of Semaphore. Now let us move from theory to implementation. In Linux, one traditional IPC mechanism is the system v semaphore. Three important functions are semget, semop, and semctl. Semget is used to create new semaphore set or access an existing one. Semop is used to perform operation on semaphores, and semctl used to control a semaphore set such as setting values, retrieving information, or removing the set. For example, look at this statement: semid equal to semget of key underscore t of 6, 1, IPC underscore create pipe 0666. Let us break this statement into individual components. Here we have sem get of key underscore t of 6, 1, IPC underscore create pipe 0666. The first argument key underscore t of 6 is the key used to identify the semaphore set. The second argument is 1. It indicates that we want one semaphore in this semaphore set. Next, IPC underscore create tells the operating system to create the semaphore set if it does not already exist. Finally, 0666 specify read and write permission bits. If the operation is successful, semget returns the semaphore set identifier. We normally store this identifier in a variable such as semid. This semid is then used by other semaphore functions. To perform operations on a system E semaphore, we commonly use a structure called struct sembuff. Consider struct sembuff SOP. The field sem underscore num specify which semaphore in the semaphore set we want to operate on. If sem underscore num is 0, we are referring to the first semaphore. The field sem underscore op specify the operation. A negative operation such as -1 is commonly used to acquire or decrement the semaphore, subject to system V blocking rules. A positive value such as +1 increments the semaphore. A particular important system V case is sem underscore op equal to 0. This means the calling process waits until the semaphore value becomes 0. Finally, sem underscore flg specify optional flags, the actual operation requested using semop function. Now let us trace a semaphore operation. Initially s equal to 1. Process P1 executes wait of s. What happens? P1 obtains the permit and the semaphore becomes unavailable to another process. Now P2 executes wait. Can P2 enter immediately? No. P2 has to wait because P1 currently holds the permit. After completing its critical section, P1 executes signal yes. Now P2 can continue. This simple sequence demonstrates how semaphore coordinate concurrent processes. So now it's quiz time. A computer lab has 3 identical printers. Which synchronization mechanism is most appropriate? Option A, binary semaphore initialized to 1. Option B, by counting semaphore initialized to 3. Option C, mutex with a count of 3. Option D, no synchronization is required. The correct answer is B, counting semaphore initialized to 3. Why? Because there are 3 identical resource instances. The initial semaphore count represents the number of available printers. When all 3 are allotted, additional processes must wait. Semaphores are powerful, but incorrect usage can introduce serious synchronization problem. One important problem is deadlock. Deadlock occurs when processes wait indefinitely for resources held by another one. For example, suppose P1 holds a resource A and waits for resource B. At the same time, P2 holds resource B and waits for resource A. Neither can proceed. Another problem is starvation, where a process may wait for a very long time without getting the required resources. We should also be careful about missing signal operations, incorrect initial values, and incorrect ordering of semaphore operations. Therefore, synchronization code must be designed carefully. Let us quickly revise what we have learned this session. A race condition occurs when concurrent access to shared data produces results that depends on execution timing. A critical section is a portion of code that accesses shared resources. A semaphore is a synchronization mechanism that controls access or coordinates execution. The wait operation attempts to acquire a permit and may block. The signal operation releases a permit or wakes on eligible waiting processes. Semaphore can be broadly understood as binary or counting semaphores. Binary semaphores are useful for one at a time access. Counting semaphores are useful when multiple instances of resources are available. So thank you on watching on semaphore in operating system. In this video, we learned race conditions, critical section, binary and counting semaphores, wait and signal operations, semaphore versus mutex, producer consumer synchronization, system V semaphore functions. This Thank you and see you in this next lecture.